Let's see if we can figure out how applying a torque is actually going to change the motion of an object. So we might imagine that we've got some object here and we are applying a force, and let's imagine that maybe at some point I apply a force up this way, and that's going to cause some rotation to the object. But I'm just going to look at one little part of the object. So let's imagine we've got some mass at a point here that is at some position vector r from our origin. And we are applying some force, say in this direction, at an angle of theta from r. Remember, the angle between two vectors we define by taking the vectors and putting them tail to tail, and then the angle theta is the angle between them when we put them tail to tail. So just keep that in mind. So here's r, bring it out here maybe, then theta is the angle between r and f when we put them tail to tail. So the torque, what is the torque? Remember, torque will be r f sine theta. Now, what is this f sine theta? Well, if we look at this little triangle here, if we decompose f sine theta, that's the opposite side, that's this side. This is f sine theta. In other words, it's the part of the force that is perpendicular to r. It's the part that is acting in this direction. We'll call this f sub t, the tangential part, the part of the force that is in the tangent direction. Say, if this were a circle, the tangent to the circle. It's only this part of the force that actually causes some kind of rotational motion of the mass, pushing it away from the origin. This component, the f cos theta, that's not causing it to rotate around the origin at all. That's giving it some radial direction, either towards or away from the origin, but not causing any rotational motion. So here we go. It's only this part of the force that is going to cause the rotational motion. So what do we have? If we apply this force F sub t on the mass, F sub t equals the mass times an acceleration in the tangent direction. So F sub t is going to give us the mass times the acceleration in the tangent direction, A sub t. Now we know that there's a relationship between the tangential acceleration and the angular acceleration. We saw that before. The tangential acceleration is r alpha. So we can write this as m r alpha. Now what's this tangential part? Well, the tangential part, which is this part, the tangential part, that is the torque over r. So this we can write as tau over r, which equals mr times alpha. Multiplying by r, we have tau equals mr squared times alpha. Okay, let's just look at that for a second. Tau equals mr squared alpha. We might think this looks, or it reminds us of F equals ma, where, remember, we have these relationships between translational quantities, x, v, a, rotational quantities, theta, omega, alpha. Well, what about some other translational quantities and other rotational quantities? Well, we have a and alpha are kind of analogous quantities. The force and the torque are kind of analogous quantities. This is the quantity that causes an object to change its motion translationally. This is the quantity that causes an object to change its motion rotationally. So F and tau, A and alpha. But what about this? We've got m here and mr squared here. What is this thing, mr squared? Well, what does m mean in F equals ma? It's a measure of the inertia that something has to having its motion changed. In other words, the inertia, or I'm going to use the term resistance, but I do not mean this in any electrical sense. I'm just using it kind of qualitatively. It's the resistance something has, or the inertia that something has, how difficult it is to change the motion of something, to accelerate it, you might say. The larger the mass, the harder it is to accelerate. The smaller the mass, the easier it is to accelerate. What about this? How does this fit in? Well, if that is a measure of how difficult it is to accelerate something translationally, this must be how difficult something is to change its motion rotationally. So some things are hard to rotate, other things are easy to rotate. For example, this pen, I can rotate this pen very easily. It's very easy for me to spin it around and drop it too. While this thing, it's much more difficult to rotate this. I can't just take this in my fingertips and spin it around like I can with the pen. It's much harder to get it to rotate. I certainly can if I use my arms and spin it, but I can't just hold it with the tips of my fingers and spin it around as quickly as I can with the pen. The pen, very easy to spin. Why? Because here the wheel has a much larger quantity in here than the pen does. This quantity is what we call the moment of inertia. And we use a capital letter I coming from inertia, to represent the moment of inertia. And what is it telling us? It's telling us how difficult something is to rotate. Very simply, that's what it means. M tells us how difficult something is to translate, to accelerate it translationally. I tells us how difficult it is to rotate or change something's rotational motion, to accelerate it rotationally. Very, very good. So we can write this then as an analogous equation, as we have F equals ma, tau equals I alpha. Very, very good. It is essentially the rotational analog of Newton's second law. Very good. So the moment of inertia, I, for a single mass, single point mass of mass m, that is at a distance r from the origin, is mr squared. Now this is, let me just back up 1 second. This moment of inertia depends on where the origin is. So if we change the origin, if we move the origin closer to the object, the moment of inertia is less. It's easier to, so to speak, it's easier to spin this thing around a closer origin than it is around a farther origin. So the moment of inertia of an object, not like the mass of an object doesn't matter where it is, but with the moment of inertia, where you put the origin affects the value of the object's moment of inertia. When you've got a whole bunch of masses, what's the total mass? How do you find the total mass? You just add up the masses of each individual object. Well, when you've got a whole bunch of objects, what's the total moment of inertia? It's just the sum of all of the individual moments of inertia. So if you've got a system of masses, say like this, m1, m2, m3, you figure out what's the moment of inertia for the ith mass. That will be the ith mass times ri squared. You find what's the distance from the origin to the ith mass, and then mi ri squared will give you the moment of inertia for that mass, and then the total moment of inertia is then just the sum of all of those. So you just add up the moments of inertia of each individual mass. If you've got some continuous object, break it down into little tiny infinitesimal masses, dm, each one at some distance r. The total moment of inertia is then the integral of r squared dm. And you could just integrate that over the entire volume. Obviously, this is going to be a very difficult thing to do for your general distribution, but under some circumstances, it's not that bad. Let me be clear about something that I said here. I'm talking about r as being the distance from the origin to the mass, but I want to emphasize this is really the distance from the axis of rotation. So if this is your axis, it doesn't matter where the origin is on here. It's always just the perpendicular distance from the axis of rotation to the point in question, not from some particular origin to the point this way. So whatever the axis of rotation is, however you're rotating around the axis of rotation, it's always measured from the axis of rotation. Let's take a look at an example. Let's imagine that we have a solid hoop. For example, something like this. So here's a massive hoop that is relatively thin. Let's assume it's very, very thin. In other words, the thickness here is negligible compared to the rest of the size. And let's imagine that we want to rotate this about an axis through the center. So we want to figure out what's the moment of inertia like this, if we were going to rotate it this way. that would not be the same as if we wanted to rotate it this way, about this axis of rotation, or this way. Now, the axis, this one would be the same as this one, right? From symmetry, we can see that. But the one through here would not be the same. Let's see if we can figure out what that is. We'll go easy on ourselves and not have to worry about too much calculus in this case. So let's imagine we've got this hoop, and we want to rotate it about an axis through the middle. So here's the hoop like this. Okay, and we're going to determine the moment of inertia about this axis here. Well, what we notice is that every single part of the mass is at the same distance from the axis of rotation. So for a hoop, every single point of this is at the same distance from the axis that goes through the middle. So the whole thing has the same value of r. So if we wanted to integrate r squared dm, r is constant. R is the same thing for every single mass. So that's a constant, we can pull that out. R squared times the integral of dm. Let's say r is we'll call the radius of this thing capital R. So the whole thing is at the same radius. We'll call that capital R. So then r squared integral of dm, what's the integral of dm? That's just the total mass. So the total moment of inertia is the total mass times r squared for the hoop. A very, very simple result. And it's basically the only one where we get a result that's the same as a point mass, unless you have a bunch of point masses all at the same radius from the axis of rotation. The moment of inertia of a hoop about the axis that goes through the center is just the total mass of the hoop times the radius of the hoop squared, mr squared. What if we have something like this? Rather than a hoop, we have a solid disk. So rather than all of the mass at the outside, some of the mass will be closer to the center and some of the mass is distributed all the way out to the end. We've got more mass in the center than all at a radius r. We would expect our moment of inertia to be less than the hoop. Let's see if we can calculate what that is. Let's imagine that we have a disk like this, so this is the whole disk here, with some radius capital R and some thickness, we'll call it L. And let's imagine that the mass density, or the mass per volume of the disk, is whatever the total mass is, m divided by the total volume, which would be pi r squared times L. So that's the volume of the disk, or the volume of the cylinder, very squat cylinder. Let's see if we can figure out what the moment of inertia is if we break this down into a bunch of hoops. So let's imagine that we take this and we cut it into some very thin hoops of a radius little r and a thickness dr, a thickness of this way, but then they'll also have a thickness here of L. So what's the mass, dm, of this hoop? Well, it's going to be the volume of the hoop, which will be, well, the volume will be, what's the area of this top? Well, that will be, imagine cutting this and stretching it out. That'll have a length of 2 pi r times a thickness of dr. So 2 pi r times dr, that's the area of the hoop here. And then times the thickness times L. Okay, that will be the volume of the hoop. And then to get the mass, we multiply that by rho. So we multiply by rho. That will be dm. What is the moment of inertia of that? di for that hoop is just, we already saw that for a hoop, it's just the mass times the radius squared. So it's going to be r squared dm. In other words, 2 pi r cubed dr L rho. Okay, there we go. And then, to find the total moment of inertia, we are going to, and I'll switch colors here, we're going to integrate di for r from 0 to capital R. We're going to integrate r from 0 to capital R. So integrate here, 0 to capital R. Integrate here from 0 to capital R. And what do we get? Well, 2 pi L rho. Those are all constants, so I'll pull those out. 2 pi L rho. And then what do we have? We've got the integral of r cubed from 0 to capital R. And what's that going to be? That is going to be r to the 4th over 4, evaluated from 0 to r, which gives us a factor of capital R to the 4th over r. So, what do we end up with? We've got 2 pi L rho capital R to the 4th over 4. So let's multiply this out, and what do we get? We get pi L rho R to the 4th over 2. Now, what is rho? Let's remember. Rho is m pi r squared L. So let's write that in. We have pi L rho, which is m over pi r squared L times r to the 4th over 2. And what do we notice? The, sorry, that's capital R squared. Capital R squared. Pi's cancel, L's cancel, 2 of the r's cancel, and what do we end up with? We have m r squared over 2. A very, very nice result. Look at that, mr squared over 2. Mr squared would be the moment of inertia if all of the mass were out at the rim, mr squared, but when the mass is distributed through all the radius uniformly, it turns out that the moment of inertia is exactly 1/2 the moment of inertia of the hoop. Remember, the moment of inertia of the hoop was mr squared. Of the disk, it's mr squared over 2. Very, very nice result. Okay, well, I think that's enough for today. What we're going to do next time is continue with this and take a look at some more of the dynamics. How do torques affect the motion of an object? And are there any other analogous quantities other than position, velocity, acceleration, force, moment of inertia? Are there other things that are analogous quantities between rotational and translational motion? We'll see you next time.